So in this exercise we are going to solve for x in this integration. So we need to first try to discover if we can solve it by substitution or we will have to integrate by parts. In this case we can see that it is possible to integrate by substitution. So if we take the inner part of this square root, 1 plus the cosine of x, and we call it g, and we differentiate this g, then we can see that it will end up being minus sine of x. And this is a very similar structure to this one over here, so we can vastly simplify the way the integral looks like. So in that case, we will do the integral from those ranges, and what we will do is the lower part is going to be the square root of g, and what we can do is, in this relationship between g and the sine of x, we can put the minus on this side, and then we'll substitute sine of x with this part over here. So minus dg dx, and then we also need to add the dx. By doing this, these two dx can cross out, and we have this very simple expression, which is from pi to 0, from minus 1 over the square root of g dg, and this can be simplified as g to the power of minus a half. So g to the power of minus a half, the minus can go to the other side, and then we just integrate as if it was just a normal simple variable. So it would be minus, we will have g to the power of minus 1/2 plus 1 divided by the same thing, so equal to 1/2 over there. This will be 1/2, and then we simplify this to minus those 2 times the square root of g. And let's not forget it has a constant over here because we have been integrating. So now we have solved the indefinite integral, which is this part over here, but we notice that we haven't finished the exercise because it's actually a definite integral between x equals pi and x equals 0. So we actually need to, with this expression, we need to substitute the values to find out the area that is in that range under the curve. So basically what we need to do is calculate the difference for both values inside the expression. So what we're going to do is we're going to take this expression, and this x is now going to be pi. So minus 2 square root of 1 plus the cosine of pi. Note that we are talking in radians in this exercise, and then because it's a difference we put a minus, and then the same expression again, but instead of pi we use 0, and then we just solve the exercise. So this minus 2 square root of cosine of pi is going to be minus 1, so all this expression is going to end up being 0, minus this with this minus turns into a plus, 2 times the square root of 1 cosine of 0 is going to be 1, and then the solution is quite straightforward. This is 0, and then 2 square root of 1 plus 1 equals 2, so 2 square root of 2, and that is the solution to the exercise. Now notice that I have not included the constant part while solving the exercise, and that's because even if I put it here, it's going to get cancelled out by this minus sign that is also going to affect the same constant on the other side. So it will just cancel out and is the same thing as if I just don't put it. So that's the reason for not including it. It's just for simplicity. But yeah. So now we're going to try and solve this exercise. We see that it's a multiplication of 2 functions, and we will notice straightforwardly that it's not a function that we can integrate by substitution, and therefore we'll have to integrate by parts. So here's the expression, just to remind ourselves, and now we need to choose what our u is going to be and what our dv is going to be. So if we follow the x-limit rule, we will realize that 3t plus 5 is going to be our u variable, so u equals 3t plus 5, and then our dv is going to be the rest, so cosine of t over 4. We're also going to need du, and we're also going to need v. So we are going to calculate that now. So du equals 3, and our v is going to be the integral of that, and we're going to solve that now. So if we take the integral, the cosine of t over 4 dt, we will see that is an integration that we can solve by substitution. So we're going to do that. We are going to substitute this t over 4 with g, and then we say, okay, so what is dg dt? dg dt is going to be, because technically speaking t over 4 is t times 1 over 4, the t goes away, we just have 1 over 4 over there, and we can change some stuff, so we will have that dg 4 times dg is going to be dt, and then this dt is this one over here, so we will substitute it. So this is the same as saying the integral of the cosine of g times 4 times dg. The 4 can go away over here because it's a constant, and then this is a simple expression. So this is the same as saying 4 times the sine of g, which g is t over 4. And that's the result for our integration. So v is going to be this over here. And now that we have everything for the integration by parts, we are going to solve the exercise. So the first part is going to be u times v. So u is 3t plus 5. The v is going to be 4 times the sine t over 4. And then minus the integral of that part over there. So integral of v, so 4 times the sine of t over 4, du, which is going to be 3, and then all of this is dt. Now that we have plugged in all the values inside the integral, we are going to simplify it. So this is just like distribution, so this is 3 times 4 times t times the sine, so that's 12 times the sine t over 4 plus 5 times this expression over here, so 20 times sine t over 4. And then this part over here, to simplify matters, we're just going to take the constants out of the way, so this 3 and this 4 go away, multiplying as a 12. And then we notice that the integral sine of t over 4 has pretty much the same structure of what happened here. It's just that the function changes a little bit. So we know that we are going to be able to integrate it by substitution, and the result is going to be 4 times the minus cosine of t over 4 plus a constant. So then this 4 will go here, so 48, and this minus will become a plus. And this is the solution to the exercise. In this exercise, we are going to integrate that expression over there. So we just have to follow the normal rules that we usually follow. So we have to use xlipid to choose what is going to be what. So once we use the xlipid, we see that our u variable is going to be the cosine of theta, and then our dv is going to be e to the power of theta. So then if we want to make the u, then that's pretty much the minus sine of theta, and then the integral of dv is going to be pretty much the same thing because it's e to the power of theta. And now we just plug in the value, so u times v is going to be e to the power of theta times the cosine of theta minus the integral that is v, so v e to the power of theta times du, so minus sine of theta, differential of theta. And normally we should already have a solution, but we still don't, because this is still not clear enough. What is actually this? So we actually need to integrate by parts again. But before doing that, I'm first going to copy this over here. So this is going to be the same as this minus with this minus here will turn into a plus. And now we are going to take this expression over here and we are going to do the same procedure for integration by parts. So now our u is going to be sine of theta, so then the du is going to be the cosine of theta. So dv is going to be e to the power of theta, therefore its integral is still going to be e to the power of theta. And then we just plug in the values again in the expression. So it's going to be u times v, so this times that is e to the power of theta times the sine of theta minus the integral of v. V is going to be that part over here, e to the power of theta times du. Du is the cosine of theta. And this is differential of theta. And now what we do is just take this expression, and since this expression is the technical solution to this part, we just substitute it there. So this is the same as doing this. And at this point, we start to wonder, because it's like, yeah, okay, so I reached the same initial point, so if I just keep integrating by parts and by parts and by parts, I could just go infinitely about it. I'm just not going to get a solution. But there's an actual reason why I decided to put it this way, and it's because we can actually solve, like if it was a simple equation. We said that this side over here is what we want to solve, and it also appears on this side. So what we have to do is just add this part on both sides to take away this part. So it's the same thing as if we add a 2 over here and we take this part away. And then what we do is we divide by 2 on both sides, and that would be the solution without first putting the c, because it's an indefinite integral. In this exercise, we need to find the area enclosed by the functions f of x equals x times x minus 3 and this function over here in this range. So the first thing that we need to find out is how the functions are going to look like and how the functions interact with each other. So we need to find out in which points they intersect. So for that, what we want to do is equal these two parts, because that will mean that those points exist for both functions. So if we do that, we will see that in order for this to be true, x has to be either 0 or either 3. So we know that the crossing points will be in x equals 0 and in x equals 3. Let's say that this is x equals 3. Now, another thing that we need to know is that the coordinates, like this is the x coordinates for those points, but since we are intersecting with this one over here, it's just going to be like exactly these 2 points over here. It's not going to be further up or further down. So what we need to do now is find out in this part over here, is the area is going to be up here or down here on the same on this side. So what we will do is realize that this is actually a positive quadratic formula. So these 2 points are actually going to be surrounding what the minimum is going to be, and the minimum is going to be here. So the function will look something like that. And because we need to reach until x equals 5, our 5 will be over here. And then what we will have to calculate then is this area over here, which I'm just going to call A, and then this area over here, which let's call it B. So then what the question is actually asking then, if we translate it this way, is calculate A plus B. So what is A plus B? So what we need to do is a simple geometric argument, that is, we take this area over here and we subtract this area over here, because that's pretty much like what we're going to do with integrals. So we do the integral of this function over here, so 0, minus this integral over here, so x times x minus 3, and this is going to be from 0 to 3. And the result of this part is going to be this one over here, but then for this one we actually need to exchange the function from 3 to 5. So this is going to be plus the integral of x times x minus 3 minus 0 from 3 to 5. That's how we ensure that the values that we'll obtain for the areas are actually positive. And then the only thing that we need to do is solve the integrals and then substitute the values for x inside the integrals and then just add the values. And I'm going to do that now. So we have now described how to find the integrals that are going to give us the area. And now what we're going to do is going to separately calculate a, and then we're going to separately calculate b. And then because it's a plus b, we're just going to add them together. So we're going to first do this part, and then we're going to do the second part. So a is going to be the integral from 0 to 3, from this expression over here. I'm just going to take this minus already out, so it's going to be there. And then this is x times x minus 3. I'm just going to simplify it as x squared minus 3x. So x squared minus 3x. And when I integrate this, this is the same minus x cubed divided by 3 minus 3x squared divided by 2 from those ranges. When we substitute, we will realize that in the 0 part, everything is going to cancel out because this will end up being 0, this will end up being 0. So I'm just going to calculate it for 3. So then this is the same as saying 3 cubed divided by 3 with this minus in front of it, minus 3 times 3 squared, so 3 cubed, divided by 2. And then if we solve this, this is more or less 4.5. And now if we go to b equals this part over there, so the integral So when we calculate this integral, we have to go from the upper range to the lower range. So since this structure is already here, we're just going to use this structure over here. So it's going to be 5 cubed divided by 3 minus 3 times 5 squared divided by 2 minus, and then with the 3 is pretty much as happens here. So we just paste that in. And this is roughly 8.66, which is the area for B. And if we do A plus B afterwards, then it's 4.5 plus 8.66, which is roughly 13.16. And that is the solution.